It's my great pleasure to introduce Ben Sigelman, our keynote speaker from LightStep. Ben.
Hi, everyone. Thanks for coming. I'm really excited to be here. This is my kind of conference. It's a very nerdy, observability-focused conference. It's like, this is what I live for. I'm really excited. So I'm Ben. I presently work at LightStep. I'm one of the co-founders there. And in my earlier days, I worked at Google for a while. I was one of several people who helped to create the Dapper project and the Monarch project. George, who worked on Monarch with me, is actually giving a talk about Monarch later today, which I'm really excited about. There's also the open tracing and open telemetry projects. I had some role in helping getting those things going. But I've basically been kind of obsessing over what's now called observability for a long time. And for this keynote, I wanted to step back a little bit and try and think about the theme of the events today around systems at scale. And what does scale really mean? And then think about observability and what does that really mean? Because I think there's been a lot of confusion about that in my mind and in other people's minds. So that's really what I'm here to talk about. And I'm looking forward to some questions at the end. I hope they're hard ones, as Jeremy was suggesting. So, right, so let's get to it. So let's talk about scaling and what I call deep systems, which is really the way I think about systems at scale. So what is scale? Here's a puddle. I think we've all seen these. Puddles are typically made out of water. I think we can all agree about that. If we scale out a puddle, we just add more water. Eventually, you get something that looks more like a lake. And if you scale out and add even more water after that, you get something even broader. You'll get an ocean, right? So this is the idea of scaling wide. This scaling wide just means having more of something. There are many examples of this, I'm sure. I don't need to explain the concept in much more detail, but for instance, you could have, wait, what's happening here? You could have a desert that's just a very wide sandbox at some level. You could have this array of solar panels is just a wide scaling version of what you'd have on like a calculator in the late 80s, right? So you can imagine things scaling wide. And conceptually, these are the simpler types of scaling in my mind. You just have more of something. And so when we say systems at scale, are we saying that the systems are just getting bigger? I don't think so. Like that's the problem. So there's another kind of scaling, which I'll call deep scaling. And there are plenty of examples of this in the natural world and in the unnatural human-created world. So here's a village. If we scale deep with something like a village or a city, it's not just that we add more of it. These things are categorically much different. If we scale further, we end up with something like a metropolis. And the key thing about deep systems, whether they be software systems or natural systems, is that they're not just bigger, they're really quite different. Other examples might be like a fractal. Have spent, I won't admit how many hours I've spent like zooming in on the Mandelbrot set and just like thinking about how kind of mind-blowing it is. Another example would be a CPU where you can just tell visually when you see a deep system, you can tell this is not simple. This is like scale for sure, but it's deep scaling that involves some self-similarity, but also a lot of differences as you go through the layers. What about software? What does it mean when software scales? Of course, it's some of each, but what does it really mean? Is it scaling wide or is it scaling deep? So when software scales wide, it looks like this. I'm sure we've all seen examples of things like this in our lives in this career. An example might be a caching service where when you get more load, you just add more servers. It's kind of just as simple as that. There are also systems that scale deep. This is a diagram of a system that doesn't exist that I obviously made in the slide software. But to make this more concrete, when I worked at Google and we rolled out Dapper for the first time, I was just kind of interested just because no one had actually really seen it before. And in the read-only systems at Google, we actually had very good coverage from early days with that because of the way that someone else had thoughtfully factored the software. So I started with a web request and just went all the way down. And by the time I got down to the lowest level of the stack for a cache miss, I'd gone down 30 levels of services to get down to the bottom of the stack, like 3-0, which is really pretty intense if you think about it. It's not just 30 services, which it was, but it was 30 layers of services. And the question is, okay, so that's Google, but what do systems in the real world actually look like? One of my least favorite things, I hope I'm not off message in terms of the Facebook sponsorship here, is when people try to copy what Facebook and Google do and do it in the rest of the world. That does make some sense in some situations, but something like Jeff Dean said at Google, obviously much smarter than me, one of his rules of thumb was that you can only design a system for about 3 orders of magnitude of scale. Because otherwise it'll be either too simple and scale up or too complicated and won't scale far enough. You can only get like 3 orders of magnitude of scale for a system to really be the right size. And Google's public number is that they're processing like 5 billion RPCs per second. So I'm not convinced that Google's systems will necessarily translate over to the real world. Like Dapper is actually the wrong system for most of the world because it scales too much and has too few features. So maybe Google has 30 layers of depth, but what do real systems look like? So at LightStep, I have some insight into this. I don't have permission to use the names and stuff, but I put together just a couple of blurred out screenshots of diagrams of organizations that are operating at some scale but aren't quite at the Google and Facebook scale. And this is one of the simpler ones. This is just a service diagram. There's nothing very complicated about service diagrams or exciting about them. I'm sure we've all seen these things. But these are some simple systems. It's about as small as they get. This is pretty typical. This is about 9 layers of depth. Here's another one where at this point, I'm no longer able to get the whole system on a slide. There are a lot of them like this. And then there are a couple like this where this thing would require like the whole room to show it, where it's thousands of services. But the key observation I'm trying to make visually, and hopefully this is obvious, is that these are deep systems. And this isn't just Google and Facebook. This is like everybody. So if you're adopting microservices, it's not like some big fan-out thing. It's that too, but it's deep. And so microservices at scale are deep, not just wide. And that's a really big deal in terms of what that means, because each layer is an additional layer of abstraction that is also an additional layer of opacity. And that's why things like observability have become such a hot topic. It's that they're really difficult. So yeah, microservices at scale are not just wide, they're deep. Okay, so that's the first thing I want to say. The second thing is to step back and think about observability. And I don't mean in terms of 3 pillars or anything. I'll get to that later. But really to think about control theory, which is where the word came from. So why do we care about it? Why do we care about observability? The word itself is kind of sad. It's like this idea that you have your hand at the glass and you're just looking at your system. You can't do anything. You're just sort of watching it. It's like super depressing, honestly. It's just like, I don't want to like observe it. I want to like fix it, So this is what the word makes me think of. It's also too many syllables, but we're stuck with it at this point. But observability, why do we care? Like honestly, why do we care about observing things? And the answer to that question has some interesting theoretical roots. So this is literally a black box. This is a system. In control theory from the 60s, there's this idea that you have a state vector, which is the internal, opaque state within your black box of your system. And it has inputs and outputs. So I've drawn these as follows. And observability is a trait of a system that specifically says observability is a measure of how well you can infer the state vector just given the outputs. So in software systems, what this is saying is that you have telemetry coming out, and the question is, how well can you infer what's happening inside the black box just given your telemetry? And that's observability. Okay, all right, fine. On the other side, and the funny thing about this is that in control theory, observability was kind of like the little stepchild. The real one that people cared about was controllability. This is controllability. So you have inputs. So these are, in a software system, things like how many replicas you want to run of a service or how you want to tune the parameters, the sorts of things that probably don't require code changes. And and the question is, given just the inputs, how well can you control the internal state? So the internal state might be things like the health of these services, stuff like that. So, to give an example, I would imagine that things like feature flags would be a great example of a controllability effort where you want to be able to affect the behavior of your software and its internal state without, actually affecting reaching in and writing new code. So when we have controllable systems, that actually, unlike the image of someone just sort of watching the system, this is what we really care about. Like we're getting hopefully paid to make things better, not just to look at them. And so observability and controllability have some kind of relationship. The relationship is actually really fascinating. From a theoretical standpoint, controllability is the mathematical dual of observability, which is something that we don't talk about that much, but that's incredibly important. And what that means, if I'm kind of going to summarize it, is that the sorts of changes you make to your system to make it more observable also make it more controllable. That's intuitively what this means, which is like this massive epiphany as far as I'm concerned. It's like, oh, okay. So that's why people get excited about things like service mesh. It's like this thing that you put into your software that allows you both to observe it and also to control it. And I would argue that other sorts of factorings that you might make to add more sanity on either side of this improve the other. And so I think part of the reason that observability is becoming so important is that whether we're using the word or not, we're actually wanting to control our systems better. And I think we intuitively understand that these two things are very closely related. And that's pretty important. So I want to make sure people think about that. And I'm about to talk about observability more in the terms that we usually use in the kind of microservices universe, but I wanted to step back and think about it theoretically first. So let's talk about observability in deep systems now. All right, so we have a couple mental models. I've had this black box, which in my mind is so abstract that we can't really have a conversation about it. There's also actual systems, like those screenshots, but that's too proprietary, so I can't talk about that either. In the middle, there's this diagram that I did this slide myself, so that's why everything is so ugly. But the idea is that you have services that depend on each other, and I like thinking of them as nested triangles. Each service is responsible for everything underneath it. Even if you don't write that code, you're responsible for it. And so the triangle is your scope of responsibility. And then the service at the apex of the triangle is the service that you manage. So this is a nice mental model in my mind of how nested services and how deep systems are actually built. And I think it's a good one for this discussion. So let's talk about managing them. Alex Hidalgo is from Squarespace is doing an entire talk on SLOs later today, which is awesome. He's an expert in that stuff, but I'm going to have one quick slide about this because I think it's so important. So if you kind of zoom into just one service and you think about that as an individual managing a service, everything really should come down to SLOs in terms of management. So again, I think this terminology I think is pretty widely deployed in our world, but the idea is that you have service level indicators, which are things like latency and errors, and then you set some kind of objective, some goal that you're going to try and hit, and that you're probably promising the services upstream from you. And those objectives are your kind of managerial objectives within the distributed system. So you might say, I want P99 latency to never exceed 1 second or whatever it is. That would be an example of an SLO. So for managing services, there are only 3 things that matter. The first one is kind of obvious, which is that you have to release new functionality. It's very difficult for businesses to compete if services don't release new functionality. So that's the thing that the product team cares about, right? But while you're doing that, there are really only 2 other things you need to do. You have to gradually improve your SLOs. So that looks like I have an OKR to make latency 20% less. Or you get woken up in the middle of the night and you have to rapidly restore the SLO into compliance. That's it. Like literally, that's all you have to do. It seems very simple if you express it this way. It's like you release new functionality, and then you improve and maintain your SLOs. If you do that, then you're doing a great job as a service owner. And that's what managing deep systems looks like. And if everyone does that job, then you're all good. The trouble is that you have to control the entire triangle. And as a service owner, let's imagine you're at the top of this larger triangle. It's an incredibly stressful position to be in. And almost, again, by definition, the psychological definition of stress, at least one that I've read, is responsibility without control. And the trouble is that you are responsible for everything underneath you, but you actually don't control it. And worse than that, you don't even really have the capacity to observe it if you're using conventional tooling. So there's that word again, control. You're stressed out because you don't have control. Control and observability are very closely related. And the reason why it's so hard to control things right now is that you can't even really figure out which of your many dependencies is unhealthy. Your service is only as reliable as its flakiest, slowest dependency. And if you can't figure out what that is and why it's happening very quickly, then you're going to be very stressed out and out of control, and probably out of your SLO as well. So the conventional wisdom about observability and software systems runs something like this. It's that Google and Facebook had problems like this. They had metrics and logs and traces, so we should too. That's basically the rationale, which obviously is kind of, from a logical standpoint, a bit of a fallacy. But let me try and break it down a little bit. So the way that this typically looks is that you have these three pillars. You try to check them all off with three experiences. So you get metrics. It looks like squiggly lines. You get logs. It looks like Kibana or Splunk or whatever. And then maybe if you're kind of doing the new cool stuff, you also get traces. And this is, I think, what people are saying when they say the three pillars of observability is that you're going to get these three things. I am here to say that you do need metrics, logs, and traces, and this is also absolutely the wrong way to think about this. Like, if there's one thing anyone comes away with in this talk is that this doesn't make any sense. Because from a UX standpoint, you're now going to have three tabs open when you're trying to resolve an incident. So that's a bad UX. And worse, the data types aren't really informing each other in this world. It's completely upside down, like totally upside down. Those data types are super important, but if you go back to if you can imagine the slide, maybe I should have put it in here again, showing the outputs of your black box. The telemetry is important. Those three data types are your telemetry. I think there are projects out there like OpenTelemetry, which I'm obviously super biased about, that are trying to create a common portable way to get telemetry out. But those are not the three pillars of your product. Those are the three pillars of your data, and there's a huge difference. The way I actually think about it is that there are two giant pipes that you already have. One is metrics. One is logs. Let's just pause here for a second. Let's imagine that you're at the top of the stack in this diagram and you're responsible for addressing some issue. Without anything additional, the cognitive load as a human being of addressing that issue, if you're not an expert in your system, or you don't happen to be one of the lucky people who's sitting in the same cube as the expert, that means that you have to be responsible for understanding the telemetry from everything underneath you. And in a deep system, because of the way that deep systems are structured, that's proportional to the square of the depth of your system. So it's like the area of the triangle that you are responsible for understanding. And as your systems get bigger, what this looks like is you paging through many, many dashboards during an incident, or kind of fruitlessly searching through logs, etc. And it's because it's not just that it's too expensive from a dollar standpoint, which it is, to centralize all this data, but you don't have the cognitive capacity to ingest that much data and weed out which stuff you actually care about, because there's a lot of false positives during incidents or analyses like this. You might try to sprinkle traces on top. and say that's going to fix it, that also doesn't make any sense to me. I think that traces are valuable, and I think looking at individual traces can be very insightful, especially for long-form performance analysis. But traces are not sprinkles. You should not think of them that way. If you just add traces on top, you haven't really addressed the fundamental issue, which is that you do need metrics and logs, and you have too many of them in your scope of responsibility to actually make any progress. The right way to think of it, in my mind, is to think of traces as context and a filter. So if traces tell you the stories of transactions in these systems, those stories provide context, and that context can be used to reduce this geometric complexity to linear complexity. So rather than understanding the entire stack, traces in the aggregate can tell you the path through your system that you need to focus on based on errors or latency. And that context can be used to reduce the search space for you as an operator dynamically to focus on the other signals that you actually care about, whether they be metrics or logs. And this is a crucial thing in that now the complexity is the height of your triangle and not the area of your triangle. And I can't emphasize enough how important this is. As these systems get larger and larger and they get deeper and deeper, you need that context to reduce your search space and the dimensionality of your search space. And that's really the value of traces, I think, as observability plays out. We're probably only like 15 or 20% into the innovation cycle for this stuff. I think traces are not sprinkles you put on top. They are the data that inform the rest of the investigation, because that's the only place you get context about transactions. So traces are the infrastructure. They're the backbone of the transactions, and that's the value that they bring. And I think we're just starting to see this happening, but this is, in my mind, why they're so important to observability. So I'm pretty much done. I just want to review. So microservices, they don't just scale wide, they scale deep, and that you have to recognize deep systems when you see them. If you work at an organization with dozens or hundreds of services, you probably are seeing this already. But we need to sort of talk about this and name this concept. And recognize it, because I think it will allow us to understand the problems that we're having in greater detail and to communicate about them more clearly. Controllability for SLOs requires observability. This is actually a theoretical truth. It's not even, you don't even need to think about software. You can just go back to the definition. Controllability, observability are essentially, they share a fate. And I think the three pillars of observability is a terrible, terrible metaphor. There are three data pipes, maybe, but they're not the three pillars. And don't think of traces as sprinkles that you put on top at the end. They're actually something much deeper. Tracing can reduce the cognitive load and create a linear problem out of a geometric one, which is pretty profound. And it must become the backbone of observability for deep systems. So with that, thank you for your attention, and I'll take any questions that people have. So.
Thanks, Ben. Yeah. Thanks, Ben. Thanks, Ben. Okay. So we have time for a few questions. We have folks with mics. Please just raise your hand. Encouragement to ask Ben hard questions. Yeah, we have one here, and we have one here. First over here.
Mic coming your way.
So when we talk about traceability, right, and most of the times we consider logging there, and what is the element of logging that we want to go on? Like we want to have debug level logging, or like focus on the primary areas, or have a deep level logging there so we can turn it on at any time and see what exactly is the problem happening and look at the issues.
Yeah, so I mean, I guess the question is essentially like what kind of verbosity level is appropriate for logging. I mean, the main thing I would say is it's probably not feasible to change it during an incident. You know, it's like you have to, whatever we're doing for observability, hopefully is running in the steady state. I know that at LightStep we've made an effort to make sure that all of our customers run the software 100% of the time in production, and I'd say the same thing if you're using, you know, Jaeger or Prometheus or whatever. I mean, the stuff should be running all the time, and same with logs. So I don't want to see people changing logging verbosity on the behalf of an incident, because by the time you're doing that, it's too late. So that's the first thing. And then, sorry, I'm losing my voice. The second thing is if we're logging about transactions, as opposed to logging about processes starting and stopping, I actually think that's what tracing is. Like tracing is just logging with extra context and transactions. And in that world, you can afford to be extremely verbose because you have some form of sampling, whether it's before the fact or after the fact, that will kind of adjust dynamically to the level of verbosity you can afford. So that's actually where I see things going. If that's too far of a jump, then I would say, like it just depends on how many transactions you're doing, but I'd kind of crank it up as long as you don't have overhead. I think not having any kind of logging data is just kind of paralyzing. So,
thanks for the question. Next one over here.
Yeah. So I guess I'm just trying to kind of come up with a formal definition of deep scaling. The main thing that you pointed out is how there's basically a dependency hierarchy. You have a service on top, and that's a certain depth of services underneath. But does deep scaling also imply growing data volumes, growing request volumes to our service, and so on?
I don't think it necessarily means that. I mean, the example of a caching service is, to me, the best example of a wide scaling software system. That can be very high throughput, but it's pretty simple. To me, usually the impetus to go to microservices is actually about human management, where you need to have the teams decoupled from each other, and so you build small teams around small services, and then that leads to layers of abstraction, and Conway's law forces you to ship your org chart. And I think that's usually the driver for deep systems more than the actual data engineering problems. So I think it's possible to have very high throughput shallow systems and very low throughput deep systems.
Thank you. We have time for one more question. I think you had your hand up next. Again, we have time. You can corner Ben and happily.
Yeah, happily, yeah.
Sure. Thank you, Ben. One of the things I guess we need your help defining better is the meaning of context, right? So when we are talking about deep systems, a lot of times we are looking for context that follows through from the top of your layer to the bottom of your layer. But many times that context is data itself, right? So what happens in tracing systems, or how should we design systems such that the data that is used for context is actually an aggregation? So I'll give you an example. Let's say I'm consuming some data and I'm doing some processing on top of that. But that processing microservice does not just operate on that data alone. There's a whole bunch of other data that it aggregates. Right? Then it processes through. So what is the meaning of context? Right? So context can get lost depending on the architecture and what the shape of your data is. Right? So how do you think about those things? How do you trace it?
Can you ask an easier question? No, I totally...
They asked me to ask.
No, it's great. It's a great question. The Dapper paper said in future work, we'll deal with coalescing requests, batching. And we never really did. I think Yuri's talking about context a little bit in his talk too. I have a kind of pipe dreamy theoretical answer for you, but in practice, I think the best thing we can do is to use systems that are sophisticated enough that, despite the fact that the context is probably lost during the batching operation, we can still see a strong correlation between the throughput issues that come from batching and the actual workload that generated that. I know that's an incredibly abstract answer. If you catch me at a break, I'll describe what I mean, but it would take like 15 minutes to talk through it.
Yeah, and if you could write that down and share it with the rest
of us. Yeah, it's a great question, though. Yeah.
I'm kidding. Thanks, Ben. Much appreciated.
My pleasure. Thank you.
Thank you.